Hello, welcome to this 8th lecture of this module on multiple random variables. And we have started this multivariate distribution, and today we will discuss about these functions of multiple random variables. This multivariate distributions we started, and what we have seen that the concept of these two random variables, that is the bivariate case, can be extended for the if the number of variables involved is more than 2. And there we started the discussion in the last lecture, and there are some more part is pending. So, we will take up that one first. Basically, the marginal distribution and the conditional distribution, these two things are pending, and we will also see one small problem on that. And after that, what we will do, we will just go to the functions of random variable, and we will take maybe this class as well as the next class we will spend on that to discuss about the what about the functions of the random variable. So, you know that the functions of random variable, we have done it for in case of the single random variable earlier, but as in this module we are discussing this multiple random variables. So, in this one in case of the more than one random variable case, we will take up, and the functions means the functions of both the random variables or all the random variables involved, that we will discuss. So, to start with today's lecture, we will start first that marginal and conditional probability distribution for multivariate random variables. So, these two part was pending in the last class. So, we will start this one first, and after that we will go to these functions of multiple random variable. The concept from the single random variable will be taken forward through the Jacobian and all. And in this also there will be some one function of two random variables we will try to take up today's class, and because there are other types is also possible. The other type is the two functions of two random variables. So, it is not only that one function from two random variables, it is possible to have two functions as well from two random variables. But anyway, today's class we will take up this one function of two random variables. Basically, we will put some put our discussion will be oriented around the sum and difference of the multiple random variables. Basically, we will take up the bivariate case as we are doing for all the cases. You know, and that first the sum and their difference. So, there are many applications you can imagine. For example, the transportation engineering, if you take towards a bridge from different source or from the different streets, it is the highways are joining. So, and the different roads are having different traffic volume. So, if we want to know that probabilistic behavior of the traffic volume at that particular point, so we have to go for the summation of the individual random variables. So, we will take up that one, and there are some of the very specific cases where it is possible to derive some simpler rules, so that easily we can do this. We can obtain the new PDF for the functions. For example, here maybe we will try to cover today's class itself that the Poisson distribution. If we take off this distribution different random variables, then if we add them up, then the resulting random variable what's its nature and all we will discuss through this today's lecture. So, first we will take this marginal probability distribution of the discrete random variables. So, now you know that we are discussing the general case. General case means when the number of random variables involved more than 2. So, suppose that there are n random variables and these are the discrete random variable, then we can get the marginal distribution of a subset of the total random variables. Say that for example, here we are taking the first k for example. So, the discrete marginal distribution of the first k random variables out of x1 to xn. So, there are n random variables. Obviously, k is a subset of this n random variables. So, then in case of the discrete random variable, this marginal distribution is given by so this p x1 x2 up to xk will be equals to the summation of the for all possible cases of the random variables from the xk plus 1 to xn. So if we do this one, do this full this is a joint PMF. If we do this summation, then we will get the marginal distribution. So basically you can see here that the concept is same. Concept is same means that what are the random variables for which the marginal distribution we are looking for. So we are looking for the marginal distribution for the x1, x2 up to xk. So the remaining random variables is to be marginal out. In case of the bivariate distribution, bivariate case, we have seen that if we want to know the marginal distribution of one random variable, then we marginal out the other one. So this marginal out means that irrespective of the remaining random variable, what is the distribution of this of the random variable for which the random the marginal distribution we are looking for. So that means that for this k plus 1 to up to n, this has to be marginal out, because we are looking for the marginal distribution for the first k random variables. So in this way we can get their marginal distributions as well. This is for the discrete case, we are going for this summation, and similarly the same thing we can go for the if it is for the continuous random variable, then we can take the same approach. Now we have to do the integration of the entire range of the remaining random variable. So here one example is given here. For example, that out of this n, again that x1, x2, x3 up to xn. So these are the n random variables are there, and we are interested to know the marginal distribution of the first one, that x1 itself, the x1, the first random variable. Then what we have to do, we have to integrate for the entire range of the remaining random variable. So this remaining random variables means the x2, x3, x4 up to xn. So that is why for the entire range we are just integrating out. That means we are marginal out the other random variables to get the marginal probability distribution. Similarly, this is the first one. So in general we can get the marginal probability density function for the any general random variable, say that kth random variable. So we have to do this integration, that is the other random variables except that xk, the other random variables has to be marginal out to get the marginal distribution for the random variable xk. So one example is given here. Suppose that the joint density, this was we take up in the last class as well for some other problem, but here we will be interested to know what is the marginal PDF of some subset of the random variables. So here there are 4 random variables are there, I, j, k, l. These 4 random variables are there. So their joint density is given by this. So this half into I plus j plus k plus l, where all these random variables have the range from 0 to 1. Now if this is the thing, then we are interested to know what is the marginal PDF of I and j. So we have to just integrate out that k and l for their entire range. That entire range is at 0 to 1. So we have to go for the integration, and if you do this integration, that is f I j for this one, you have to integrate out that k and l. So here for all the random variables this range are same. So you have to if it is not, if the ranges are, if the support of that random variable is different, then you have to take care of that range of this integration. That is, for example, the first one we are doing it with respect to the k. So as we are doing it with respect to the k, and this k range is 0 to 1. Similarly, then after we take it, if we integrate out, then we are doing the same function with respect to that l for the range of the l, which is also here 0 to 1. So we are doing this integration, and by this this is simple one. So if we put this integration limit, we will get the new function, which is half I plus j plus half plus l, and again for this one we do this integration with respect to l, and we get this form, and after that we get the final form as half into I plus j plus 1, and here also this range for this I and j are 0 to 1. So, now we see in this function, which is obvious that it is irrespective of whatever the value of this k and l. So, here this function should, in this function k and l should not appear, because this is also mathematically also obvious, we have integrated out that one. So, this is the marginal distribution for this I and j, which is half into I plus j plus 1 for the range I equals to 0 to for the range of I from 0 to 1 and j also from 0 to 1. Now, the conditional probability, this also we have discussed in case of the bivariate one. Here we are taking up that for this n numbers of this random variable. And first, if we take that discrete random variable case, so conditional probability mass function for the PMF, the conditional PMF of any of the random variables in a multivariate discrete random variables given the other variables is expressed as this. So, here you see that the distribution, the conditional distribution of the random variable k plus 1, k plus 2, k plus 3 up to n. So, for these random variables we are looking for the conditional PMF given the condition is given, the condition is that we know that x1 to xk. So, for this subset, that is first to kth random variable is known. So, based on that condition, what is the distribution for the remaining random variables, which is k plus 1 to xn. So, this is now you know that the probability of this x k plus 1 equals to x k plus 1 in this way up to xn equals to xn on condition x1 is equals to x1, x2 is equals to x2, and there are some specific values for this random variable starting from the first to kth random variable. Now, you know, if we for the bivariate case, if we just want to relate how to get this probability, it is the directly what we can write is that first of all, this is the joint PMF for this all the random variables starting from x1 to xn. So, that should be the normalizing factor here should be the marginal distribution on which this distribution is conditioned on. So, now this distribution is conditioned on the subset of this x1, x2, x3 up to xk. So, we have to get their marginal distribution. So, that marginal distribution should be used as a normalizing for this joint distribution, joint PMF to get the conditional PMF for this xk plus 1 to xn. So, this denominator here you can see that this is the PMF for the x1 to xk, which is the marginal probability, marginal joint probability distribution between x1, x2, x3 up to xk. So, in this we will get the conditional probability mass function. So, it is not only that. So, here one example is shown, means one specific case, not example, the specific case is shown where we are taking that k plus 1 to xn on condition of x1 to xk. So, it is not necessarily that the random variables that we are considering it should be one after another. It is not that case. You can pick up any random variable of your interest and condition on whatever. So, this k is a general notation. So, you can even pick up that x1, then x4, then x9. So, remaining so it should be condition on the remaining random variable, and accordingly you have to say that which marginal distribution you should have before you can get this conditional distribution. Similarly, if this is a continuous thing, then you have the continuous random variable, then also for the k plus 1 to xn random variable condition on that x1 to xk, you have to get that the joint distribution divided by the marginal distribution of the random variables from x1 to xk, that is on which this conditional probability distribution is conditioned on. So, this is the marginal joint distribution of the remaining random variables. So, with this one more thing that we have also discussed in case of the bivariate one, that we can get the joint distribution if we know that conditional distribution and the marginal distribution if we know, then we can get the joint distribution. So, here is that one is shown here. that is this is the conditional this is a joint distribution. Now the joint distribution between the random variable x1 x2 up to xn, this one can be expressed in a general term of this, that marginal of the x1 multiplied by the conditional of x2 given x1, that multiplied by the marginal of the x3 given x1 and x2, and in this way it will go on. So the general term of this series will be that the conditional distribution of xk given that x1 x2 x3 up to xk, and finally at the last the marginal distribution of xn given that the random variable starting from x1 to xn minus 1. So this is a general term to get that joint distribution between this x1 up to xn. You can recall that in case of the bivariate one, that is when the n equals to 2, so only two random variables are there, x1 and x2. So this expression, basically the first one, if we just take up, that was the expression that we discussed in case of the when we considered only two random variables x1 and x2. So when we are extending for this n numbers of random variables, so this is the way the expression get expanded. And finally the independence between the n numbers of random variables. Earlier we discussed the independence in case of the two random variables x1 and x2, and there we have discussed that if and only if, of course, that the joint distribution between two random variable can be is equal to their product of their individual marginals, then we can say that these two random variables are independent. Now in case now if we just extend the same thing to the n numbers of random variables, then again it will be the concept will remain same, that is, if the joint distribution of those n numbers of random variable can be expressed as their product of their individual marginal distribution, then only we can say that these n random variables are independent to each other. This is explained here. So if x1 x2 up to xn are called the mutually independent random variables, and this is possible if and only if their joint density is a product of their marginals. So this is a joint density from x1 to xn, and from this x1 x2 x3, which is equals to their product of their individual marginals. So I x f x I varies from 1 to n, that means for all x1 x2 x3 up to xn. Okay, so with this the properties that we wanted to know for the in general case, that is for the n numbers of random variable, that is over, and next we will take you through the different functions of these multiple random variables. First we will start with the two random variable case, and then again following the similar way we will extend it for the more than two random variables as well. So to start with the functions of multiple random variables, in most of the problems we generally face more than two random variables are in relation, and so therefore we need to know the functions of the random variables. So that once these functions of these random variables are known, then how we can get the PDF or obviously after that CDF of the functions of the random variable. So in earlier module, in module 4 particularly, the functions of the single random variable were discussed. So there also we understood the basic concept, that is, if the x is a random variable and we generate some a function of that x, that is if y equals to gx, then that function y, that is also another random variable. So if that is also a random variable, then we know that how to know that different properties, that is different properties means if we know the PDF of that function, then everything is known. So that we discuss now here. Now in this module we will be take up that two or more random variables, and this will be explained. And the concept that we used earlier in case of these functions of single variable are also applicable in this case as well, and that we will take you through one after another. Basically, here the two situations can happen. Two situations means that, as you know, that we are first of all we are taking the bivariate case. So, for the two random variables we can have one function, or we also may have two functions of the two random variables. So, first of all we will take up this one, that is one function of two random variables. And so, one functions of two random variables means here, suppose that two random variables are there x and y, then the x plus y is one function. So, which is using both the random variables. So, x plus 1, x minus 1, like this. So, for this discussion, you know that this f x y represents the bivariate PDF, and the p x y represents the bivariate PMF. We will use this one to know that what is the PDF or PMF, as the case may be, for their functions. So, let us consider that there are two random variables which are that x and y, and this x and y is having a function which is represented by the gxy. So, g is the functional form, and which is basically giving the giving another that function, that gxy itself is a random variable. So, suppose that this gxy is equals to z. So, now we are interested to know the properties of this z. So, if we know that PDF, that is that f z of z, or if it is discrete, then it is p z of z, that is PMF. So, these two things we have to know, and what we know is that we know their joint distribution, that is f x y, the joint PDF or joint PMF, that we know, and we are interested to know what is this f z of z or f p z of z. Now, if we want to know that this PMF of the z, then this PMF of z is explained is expressed as this, that Pz of z is equals to the summation of their joint PMF for all the possible values of its function, that is g xi yi. Now, this I can vary. This xi yi is the combination for this all feasible combination, and all feasible combination, this is we are talking about in case of the discrete, because only few specific points where the probability is defined. Now, once we know this PMF, then that PDF is again just that for a particular value it should be less than equals to that z. This will be obviously small z, because this is a small z. So, if it is less than equals to this one, then if we sum it up, then we will get that they are corresponding CDF. Similarly, for the continuous case, for the to get the PDF of this z, we have to integrate for the feasible range of this function, that is g a x y, in this way with respect to that dx and dy. So, double integration we have to do, as the number of random variables involved are 2. This is a bivariate case that we are talking about now. Similarly, once we know this one, if we want to know that CDF, then CDF should be, this should be less than equals to that specific value of z, and over that range if we just integrate both these random variables x and y, so then we will get what is its corresponding CDF. We will just see it in case of a particular application in a minute. That is, we will just take the sum and difference first, which is also there are many applications in civil engineering, particularly in the transportation engineering, that we will talk about. But before we go to that specific functions, we can just have a look that what are the different possibilities of the single function out of two random variables involved that is possible. So, here are some glimpse of that one. So, that we are talking that the first what we have expressed is that the summation, that is x plus y, this gx can be that their summation of the random variable involved, or it can be the difference, that is x minus y. Similarly, it can be the ratio, that is x by y, or their product x y. Some trigonometric function of that one, that is tan inverse x minus x by y, or it can be the ratio of the minimum of both the random variables divided by the maximum of both the random variables, or there could be some other algebraic operators, square root of x square plus y square, or simply the minimum of both the random variables or maximum of random variables. We are not saying that this is the only possibility, there could be some other, but just to show you that some of the things that we may be interested. We will pick up this this summation and the difference first to explain it in details, in the sense that just to show a pictorial view how or what should be the integration limit, on what we should go for the integration to get the behavior of the function that is based on these two random variables. So that we will take up first, and similarly the same concept can be used for the other cases as well, what we have shown just now. So, to start with, let us take that the sum and difference of the multiple random variables. So, that let that x and y be two random variables, there will be one s, and there exists a function which is that z equals to x plus y. Now, if this is the function, then that f z is equals to, that you know from the CDF, that this is the probability that the random variable z should be less than equal to the specific value of this z. Now, this z, as we have already denoted that z equals to x plus y. So, this means that this probability x plus y should be less than equals to the specific value. Remember that, as we have told earlier also, this lowercase letters are the specific values of the random variable and the uppercase letters are the random variable itself. So, this one we can just, so you can see this should not be the capital Z, this will be the small z. Basically we are just taking from this equation to here. So, this will be the small z, which is the specific value of their of this random variable z. So, the probability of the y less than equals to small z minus this x, and if we want to know this probability, then we have to do the integration over some range of the plane xy, that we will explain in a minute. So, that range now we will show that how it comes from this minus infinity to this z minus x, and this is with respect to the y, and that should be integrated with respect to the minus infinity to plus infinity. This is of course in case of this continuous, and for the discrete, for whatever the possible cases where that xi plus yi is equals to that z, or is less than equals to z, rather that less than equals to z, for that all those feasible combination of this xi and yi, we have to add up this PMF to get their that cumulative probability distribution. So, now to see this range here, some pictorial representation is shown here, that so on the figure you can see that by integrating the horizontal strip, that is horizontal strip that we have taken out. So, this line that you see, this is basically showing you that x plus y equals to z. Now, this shaded area, that light blue including this strip as well, this area is nothing but which is the x plus y less than equals to z. Now, to get this cumulative distribution function, we are interested in this area. So, as I have told that x plus y should be less than equals to z. So, this is that area that we are talking about. So, probability over this one should be integrated. Now, this obviously we are talking with respect to the continuous random variable, and if it is a discrete, then what will happen in this shaded area, whatever the points are there, points means the combination of this xi and yi, that we have to add up. So, now there are two possibilities. You can take a strip like this. So, for this strip, basically this area going to the going up to the minus infinity. So, this strip is basically from the minus infinity to that x equals to z minus y. Now, this strip, if we just integrate out from with respect to the y, if you integrate from this minus infinity to plus infinity, so that is eventually covering this full shaded area to get this integration. So, for the x, the limit is from minus infinity to z minus y, and for the y, the limit is from minus infinity to plus infinity. So, this is what you are what we have just shown here as the integration limit, that is for this for this x. So, this will be dx dy. So, for this x, so this would be dx dy. For this dx, the limit is from the minus infinity to z minus x, and for the dy, the limit is from this minus infinity to plus infinity. So, this is only one possible case that we have shown. The integration could have been also done taking a vertical strip. So, in this vertical strip, then you have to do the integration with respect to the y first, and in that case the range will be from the minus infinity to that y equals to z minus x. So, y equals to z minus x. So, for that range, and for the x, that you can see that from the minus infinity to plus infinity. Basically, the diagram should have been shown taking the strip like this, because here the limit that you can see, that is written that z minus x. That, so, if you just see it here, what I am talking about, suppose that these are the two axes, one is this x and other one is the y, and what we are looking for is this line where this x plus y is equals to your z. So, x plus y less than equals to z means we are just talking about this area. Now, if we just take a strip like this, okay. So, this is basically going to this minus infinity and going up to the area. If we just take this y equals to minus infinity to this one, to this point, this point is y is equals to z minus x from this line. Now, this strip you are basically taking it from the minus infinity to the plus infinity. So, this is the range for this x. Basically, with respect to this diagram, if you see this this equation, then it will be more clear. There is y, it is minus infinity to z minus x, and for the x, it is minus infinity to plus infinity. Okay. So, this way, if you do this one, then you will get, when the x and y are continuous, it can be expressed as from this minus infinity to infinity f x y dx dy, and this one, when you are talking about this z minus x, which is replaced by this y, that means the g inverse, the function inverse that we are talking about, where this g inverse is the g inverse of x z. By changing the variable of integration from y to z, what we can get also is that this f z z from minus infinity to plus infinity, from this minus infinity to the z, this function with respect to this joint density, taking this x and g in inverse multiplied by their this partial derivative with respect to z of that function dx dz. Now, maybe it may not be that straightforward to understand at this stage, because basically this is a Jacobian that we are talking about, and this will be, and why we are just talking about this, as you know that the way the integration that we are taking and integration limits that we have discussed, it will be more easy to do this integration in this way. But you know that this is a single function that we are talking about. Next, when you will go to these two functions or even more, then what will happen, we will see that this taking this Jacobian will be more easier, and this one also we have discussed earlier when we were talking about the single random variable, and in that single random variable we have seen that how the Jacobian can be useful, and it will be even more useful when we are talking about the two or more functions. So, that is why it will be more clear when we will be take up possible in the next lecture, the two functions out of these two random variables. That time we will just see it again. So, so for the time being, so this can also be expressed, that is the PDF can also be expressed through this integration over the entire range with respect to the x by taking this Jacobian, that is d partial derivative of g inverse dou z, and if you take this inverse is equals to this, again you can do it with respect to the y as well. So, thus this f z can finally be, so which is a PDF, can finally be shown as this for this entire range of this dy. You can just replace this x as this z minus y, and also the opposite is also possible, that is you can replace that, okay, here it is, there you can replace this y also, that z minus x with respect to dx also you can do. Similarly, if it is that discrete random variable, then this will be the summation for all possible xi of their joint PMF. This would be P, small p, joint PMF, and this is by replacing that yi, that is for all possible yi, and this will be that PMF for that x and y, between x and y. Now, if x and y are independent, you know that for this one, if x and y are independent, and if we are interested for the summation, the distribution of the summation, then this can be explained as minus infinity to plus infinity fx z minus y multiplied by fy z minus y dy, because you know that their joint is now the product of their individual marginal. So, fx x, and the x is replaced by that z minus y. Similarly, for in case of the discrete random variable, this will be for all possible x y. We can just write that for this px of this z minus y and py for this y. For both these cases, that is for the continuous and the discrete, you can even replace that y and do this integration with respect to the x also, that you can understand from the previous slide. So, now we will take up one example, and this example is based on the traffic control. Traffic control means here that there are some waiting times, and for between two destinations, the passengers are traveling from one point to another point via two mode of transport. Say the first segment, they are traveling by one mode of transport, say by bus, and the next one they are traveling by train. So, if we just have to model their waiting time for the full sector, for the full stretch, in considering the time for the bus or the waiting time for the bus as well as for the waiting time for the train, and then there is a specific application that the total waiting time should be the summation of these two random variables. So, these two random variables means that we are considering the waiting time for a particular passenger for both the mode of transport or the random variables. So, what is the total time that a passenger has to wait? So, this type of problem, if we want to model, then the theory that we have discussed just now, that summation of two random variables is important. Similarly, so why we have taken up this one is that there is an waiting time, and this waiting time can be modeled through that exponential distribution, and so that can be easily shown here through some calculation. This can also be shown in case of the suppose the two river streams are merging at a point, and we know the nature of the flows for both the tributaries, and so what is after joining, so what should be the nature of their distribution. Again coming back to the transportation engineering, so if suppose that there are two routes are connecting to two cities, and both the cities, so the roads are coming and joining to a point where it might be critical with respect to the traffic volume. So, if I know that the nature of the traffic volume for both the roads, and so we can from there we can assess what should be the critical condition at the junction by knowing the nature of their individual traffic volume for both the routes. So, these are the type of applications that you can see in the different areas of the civil engineering. So, one such example is taken here for the passenger waiting time. So, a passenger after reaching a bus station has to wait for the arrival of a bus. After traveling in the bus, he must remain at a railway station until a train arrives. So, you can see now there are two mode of transport. First one is the bus, and second one is the train. Circumstances are such that the times in hours. So, times what is explained in terms of hours. This is the x and y that has to be spent by the passenger awaiting for the bus and the trains respectively. So, the waiting time for the bus is denoted as x, and waiting time for the trains is denoted by y, and these are obviously considered to be the random variables. So, the travel time in two modes of transport are constant for a particular short segment traverse, and the PDF of their both these random variables x and y are given by this exponential distribution, which is that 0.8 exponential minus 0.8x for this x greater than or equal to 0, So, this so that that here the lambda is equals to 1 by so lambda is equals to 0.8. So, the mean waiting time, if you see for this first mode of transport, that is for the bus, it is 1 by 0.8. You know that for the exponential distribution the mean is 1 by lambda. And similarly for the train, that the PDF is shown as the 0.4 exponential minus 0.4 y. For the support for this random variable y is also again greater than or equal to 0, because the waiting time cannot be negative. So, assuming that the arrival of the bus and the trains are independent, determine the PDF of the total time spent by a passenger in awaiting the transport. Since the arrival of the bus and trains are independent, the total time spent by the passenger in the waiting transport is z equals to x plus y. So, so this is a new random variable z, that the nature that we are looking for. So, what should be the PDF of this z? Now, as we have told that now this is a little bit more, even more simpler, because we have considered that these are independent. So, as these are independent, now their joint distribution, because I need to know their joint distribution from the theory whatever we have seen just now, that we need to know what is their joint distribution for the two cases of the joint bivariate PDF. So, that PDF we know, and from there we will calculate for the specified range, we should do that integration to know what is their nature, that is PDF or CDF. So, similarly here just what we have seen, that if they are independent, then we can do for this one, that is their joint will be the product of their individual marginal, that is fx and fy. So, fx now is replaced by this y, that is z minus y, and fy is the y. Now, we will just put that now this integration limit. So, as we are talking that over the entire support of this random variables. So, the entire support here is this, that is when we are talking about this z, the total time for the lower limit should be 0. So, x plus y is giving you the z. So, x plus y as it is giving the z, then obviously the lower limit is 0, because the waiting time for the passenger, even it is for the both the transport, it will always start from 0. So, that lower limit is 0, as the lower limit for both the random variables are 0. So, now we have to see that what is the upper limit for this y against which we are doing the integration. So, this upper limit of the y can never be more than z, because that this z is nothing but is equals to x plus y. Now, even so, minimum value that x can take is 0. So, that means the maximum value that the z that if it is the x, that is for that equation, that is the x plus y. So, that possible range for this y, the maximum upper limit that the y can take should be equals to z. So, this is what is shown as the integration limit between this 0 to z. And now the remaining part is straightforward. So, we have to just put this PDF in individual PDF for this x, that is 0.8 e power minus 8 in place of x, we have to write that z minus y, and this is for 0.4 e power minus 0.4 y, and for this range we have to do the integration. This is what is done here, that is for this 0 to z 0.8 e power minus 0.8 z minus y, which is multiplied by the other marginal PDF, that is 0.4 e power minus 0.4 y. And if we take this one just after following few steps of this integration, that is we can take out this 0.32 e power minus 0.8 z, and integration over this 0 to z e power 0.4 y. So, this y you are just taking care the 0.8 y as well as this minus 0.4 y. So, which gives this 0.4 y, and if we do this integration for this range, so it will come like this, and if we just put this one that is 0.4 z minus 0.4 e power exponential minus 0.8 z. So, this 0.4 is taken out. So, finally, it comes at 0.8 e power minus 0.4 z minus e power minus 0.8 z, and the range of this z is of course from 0 to infinity. So, this is the complete definition of this z. Of course, this range is also important, that is z is greater than or equal to 0, that you can understand. So, so as this is a PDF, and if everything is all right, then you can do once this one as an integration from 0 to infinity and check whether the integration is coming out to be 1. So, that is the basic requirement for this function to be a valid PDF. And as you know that for whatever may be the value of this z, as the nature of this function is, this is always greater than or equal to 0. So, first condition is satisfied. Second condition, you can check whether the integration from 0 to 1 0 to infinity is becoming 1 or not. And now, if we just take it through this more general one, that is in case of this z is equals to ax plus by. So, there are instead of simply we are adding up, we are just multiplying it by some coefficient. So, x by the coefficient a and y by the coefficient b, then what we get, that y is equals to z minus ax by b. So, this one, this derivative that we get is equals to 1 by b. So, from this again from this that basic equation, that is fz should be equals to that mod of this derivative from this minus infinity to plus infinity fx of this z minus ax by b, which is dx, or we can even that replace that other one, that is in case of x equals to your z minus by by a. So, in that case this derivative will be equals to 1 by a. So, this is then the integration will be with respect to y. So, this also we can do. Then if the x and y are statistically independent, then the PDF of z is again, you know that whatever the joint distribution that we are writing here in this form, you know that this joint distribution will be the product of their individual marginal. So, we have to just write that fxx multiplied by fy of y, and y is nothing but z minus ax by b. Similarly, instead of replacing the y, we can replace the x also. Then we have to do this integration with respect to y. So, now similar to the summation of the multiple random variable, left x and y are the two random variables, and there exists a function which is that x minus y. So, this is the difference between two random variables here, and of course, the x is greater than or whatever, that is x minus y in general case, that is z is the difference between two random variables. So, here also following the same procedure that we have done for this summation is that now here the limit, that is that upper one for this first with respect to dy, it should be minus infinity to z plus y. And after doing this one, we can get that from this over the entire range of this x, that is you are getting this joint distribution for this z plus y. So, you are replacing that x, and this is a double integration for there over that entire range of this x and y. Here also means the same pictorial representation, that is x plus y. So, this line is basically is showing that x minus y equals to z, and this side is equals to your that x minus y less than equals to z. So, up to this you have to do the integration. Similar to the earlier discussion, you can take a strip either in this direction or in this direction, and for both the cases suitable with the suitable integration limits, we can do the integration to get their PDF. And again, if they are independent, then we know that their this joint distribution will be the product of their marginal, and when we are replacing this one, obviously it will be the z plus y to get that fx of x and this fy of y, and then we will do the integration over the entire range of y in case of the continuous. And for the discrete also, then this for the individual PMF we can multiply for all possible sets of this x and y to get the if the random variables x and y are discrete. Now, as I started with that, if the random variables, in case of some specific random variables, if we just add them, then there are some specific results may come up. So, there are many such or few such distribution where these summation are straightforward. First of all, we are taking if the distributions are Poisson distribution, that is both the random variable follow the same Poisson distribution with, of course, it might have the different parameters, but the distribution nature is same. So, if the random variables which are x and y are statistically independent and have the Poisson distribution with the parameters lambda and second one is the mu, then so that you know that if it is a Poisson distribution which is a discrete distribution, and this Px x is equals to lambda t power x by x factorial e power minus lambda t, and for this Py y equals to mu t power y by y factorial e power minus mu t. So, if this is the these are the distribution, then if we have the functions like x plus y, then following the same equation that we have shown just now for the in case of the discrete, obviously this is a discrete distribution. So, we will just put these functions and just we get there for all feasible x, if we get the summation, then by this fifth step we will get another distribution which takes the form like this, that is lambda plus mu t power z by z factorial e power minus lambda plus mu t. Now, if you see this one, this is also takes the similar form of this of the Poisson distribution, and of course, that parameter has changed now. The parameter what is here is this lambda plus mu. So, the sum of the random variables with the Poisson distribution is also a Poisson distribution with parameter lambda plus mu. So, similarly we can extend this one. So, in case of these are two random variable which are Poisson distribution, if there are more say that n numbers of these Poisson distributions are there, and this z is nothing but the summation of all of them, then this summation, this z will also have the Poisson distribution with the parameter, and that parameter lambda z should be equals to the summation of all the parameters of this Poisson distribution. But the difference of two random variables having the Poisson distribution is not a Poisson distribution, that also you can check whether the same, so whether this type of form is coming or not, that you can check. So, the difference is not a Poisson distribution, but so far as the summation is concerned, we get the similar distribution with the where the parameter is also the summation of the individual parameters. So, so in this lecture we have discussed about the we have started with this discussion for the multivariate random variable first for their marginal distribution and conditional distribution, and after that we have started with the functions of multiple random variable, and in this lecture we have covered mostly the one function of the two random variables, and in the next lecture we will take up the two functions from two random variables. Thank you.